everybody. Thank you for having me here. My name is Roberto, and I'll present on our work on the security analysis of the Ethereum for choice specification, which is a fundamental component of the consensus layer of Ethereum. And this project was supported by an Ethereum grant and was done together with my colleague Chenyi at the Dependable Distributed System team at Consensus. A quick overview of the agenda today will provide a few basic concepts about the Ethereum consensus protocol that we will need to understand some of the bugs that we have identified and the fix that we have applied. Then we'll discuss the bug discovery fixing process, how it can be improved. We'll go over some limitations of our approach, future work, and we conclude with key takeaways. So moving to these fundamental concepts of the Ethereum protocol. As most of you know, we have our DIA beacon chain, which is composed of blocks. Blocks are organized into epochs. Epochs are organized into slots. And some blocks play a special role. These are called checkpoint blocks. And for simplicity today, we say they are the first block in each epoch. Now, a checkpoint is actually a pair of a checkpoint block and the epoch where that block is. So for example, checkpoint 0 is a pair of block 0 and epoch 0. Block 32, so checkpoint 1 is the pair of block 32 and epoch 1. And checkpoints are fundamental to how validators vote. So Ethereum validators cast two types of votes. One is what is called an FFG vote, which is what we are most concerned about today. And FFG votes are votes between a source checkpoint to a target checkpoint. The other type of vote is what is called LMD ghost vote, and these are votes for a block. A very important concept in the Ethereum consensus protocol is the concept of supermajority link. And we have a supermajority link when the FFG votes for a link are cast by a set of validators with a stake that is at least 2/3 of the total stake. And if you start from the genesis block, you follow these supermajority links. Any checkpoint that you find is a justified checkpoint. Now, when a justified checkpoint has a supermajority link to a checkpoint in the next immediate epoch, that checkpoint is finalized, and so is the block. And when you have finalization, unless things go very bad, you are sure that that block and all the chain will always be canonical. Now let's look at how validators vote. So let's take this picture. One important concept I forgot to mention is that in blocks also include votes. So each block carries a set of votes. So we have this situation where you have a chain with a fork, and the first question that a validator asks itself is, which chain should I follow? And the answer to this question is given by the fork choice specification, or fork choice rule, which says, essentially, start from the highest justified checkpoint, filter out blocks that are not good. This is a detail we don't need today. Then go down the branches, always following the branch with the highest amount of attestations in terms of weight, until you find a leaf block. And that leaf block is your head of the chain. Now, let's say B95 is our head of the chain. Then we follow the honest validator guide, which tells us how to vote. And the way we have to vote, we need to take the latest justified checkpoint according to the state of the head block. This is our source checkpoint, and the target checkpoint is the latest checkpoint in the chain. So for example, in this case, the latest justified checkpoint in the state of B95 is a B32.1, and the latest checkpoint is actually B64.2. So this means that the vote that the validator will cast will be between checkpoint B32.1 and checkpoint B64.2. So last concept before looking at the bugs. As most of you know, the Ethereum protocol protects itself by punishing those who don't act according to the protocol. And there are two major punishable offenses. One is what is called double vote, which is when a validator votes twice for a checkpoint for the same epoch. The other one, which is what we'll most need today, is the surround vote, which is when a validator has two votes, one of which surrounds the other in terms of number of epochs, which is what you see in the picture. So now we have everything that we need to look at the first bug that we identified in the for-choice specification, which has been fixed. So the resolution is not great here, but so trust me in what I'm going to say. Let's start with the first image. So we're at this situation. As you can see, there are two supermajority links. And the block B96 is the highest justified checkpoint. So a validator that votes in this scenario will vote between B96 and B128, as B128 is the latest checkpoint. As you can see, there are no blocks in epoch 2. This can happen, network splits, as Danny was speaking before. You never know. Things can go very widely. What happens then is that actually you receive blocks for epoch 2. And these blocks for epoch 2, they carry votes that create a supermajority link between block B32 and B64. Now what's going to happen, then we receive block B160. And in block B160, the latest finalized checkpoint, in this case, is B32. As B32 is a supermajority link to B64, and B64 is the latest justified checkpoint. Now, in the code on the left-hand side, you can see what the for-choice spec used to have encoded as a rule to update the latest justified and finalized. And the rule was, if you see a block with a latest finalized that is higher than the previous one, you update both, the latest justified and the latest finalized. Now, if you apply it to this scenario, it means that because you receive B160, where the latest finalized is a B32, which is higher than before, you update both latest finalized and latest justified, meaning that the latest justified, which was before B96, moves back to B64. Now, as we said before, when you vote, you start from the latest justified, which is B64. Now, the only leaf block is B160, so a validator will cast the vote between B64 and B160, which is a surround vote, compared to the one above, which was between epoch 3 and epoch 4, as the last one is between epoch 2 and epoch 5. Lucky enough, so basically an honest validator doing the right things can get slashed. Good news, the fix was very simple in a way. All we had to do was to remove this line from the spec. There are a few other things we had to do to ensure that we didn't create other issues, but the fix in this case was simple. Of course, someone might say, well, validators have anti-slashing protection. That's true, so they don't get slashed. They can incur penalties because they don't send attestations. And if you have too many validators doing this, you can end up in a situation where you cannot progress. You cannot justify new blocks. You cannot finalize new blocks, which is pretty bad for the network. So this is the first bug that we identified. I'm not going to go over this one. This slide is just to communicate that this bug has a very complex scenario to be that the network has to follow in order to trigger a surround vote. And this bug was created in a way by a fix to something else before. And all this leads me to the next chapter, which is this process where you have a spec, you find the bug, you fix the bug, you have a new spec, and now you find the bug that perhaps it's caused the previous bug. You fix it, you get a new spec, and you are in this situation which is safer. The one where I have a bug that I know that there is a bug, or the last one where perhaps there is a new bug that I don't even know about. So what we propose is, well, let's take a different approach. Let's agree on a set of properties that we want the protocol to guarantee, and let's build a mathematical proof that shows that the protocol always guarantees, the specification always guarantees these properties. Now you can have two scenarios. The proof says everything is good, great. You can also have a scenario where you find issues, as we did. And in this case, you fix the spec, you do the proof again, and hopefully the proof will say you're good to go. Now, this might seem similar to the cycle we saw before, but there are two fundamental differences. First, with the approach that we had before, we could never end up in a situation where we could say that property is guaranteed by the spec, no corner cases with respect to that property. And also, when you build a mathematical proof and you find an issue, you get a lot of information that you can feed into the fix. So it's quite likely that your fix will actually then pass the following proof. So a bit more on this. The main difference between having mathematical proof and testing is that mathematical proof can be exhaustive. We can consider networks of any size, any type of behavior, any type of scheduling. If a property is ensured, we can prove that it's ensured. And if a property is not ensured, your proof will fail somewhere. So you detect that, that there is a bug, which you cannot do in testing. You can't enumerate all the cases. What we did was slightly different. We actually applied this to a subset of the properties, as we wanted to have this done in time for the Capella fork. And in terms of properties that we proved, we showed the non-slashability property, meaning that an honest validator can never slash themselves. Honest viable head, which says that if the network is good, a block proposed by an honest validator within the current epoch is always considered as possible head of the chain. Doesn't mean it will be chosen, but at least it's not filtered out. And that block freedom, meaning that we can never end up in a state where it's impossible to make progress. Does not mean we'll make progress, but at least we know that we can make progress. There are other properties that will be good to prove, and that's part of future work, potentially. No malicious rewards, which will be that blocks proposed by honest validators are always canonical, which is a stronger version of the honest viable head. Liveness, simple way, say, a chain of finalized blocks created by honest nodes is ever growing, which is a stronger version of the block freedom. Irreversible local finality, meaning that in the local view of a node, a finalized block is never reverted, even though the majority of the nodes all the nodes are dishonest. Existence of confirmation rule, which we're working on now, basically having a rule that allows you to work on the available chain and have determined that under good network condition, a block will always be canonical, even though it's not finalized yet. And dynamic reliability, basically showing that the protocol is correct, even though some of the honest node might go offline, might go asleep sometimes. So this leads me to limitations and future work of our approach. Of course, the first one, we have improved everything, that's true. But there are properties we can work on, as we are currently doing on the confirmation rule. And also, if some of the properties are shown not to be true, you can work on the protocol and modify it so that it ensures those properties. There can be error in the manual proof, correct, that's true. That's possible. Well, the next stage will be have mechanized formal proofs. So you have a machine that checks that your proofs are indeed correct. Some of the properties might be missing from the list. Well, this is a hard one to fix. If you don't know what you want, it's hard to prove that the protocol satisfies what you want, as you don't know it. So the only thing here is to keep in touch with the community, making sure that one keeps this list of property relevant. Of course, as Danny mentioned before, there can be bugs in the implementation. Well, there is work currently done by also another team in Consensus on improving the testing framework, which increases the chances that if there is a bug in the implementation, it's actually caught by the testing. And finally, true, sometimes we do model the system, and model of the system is an approximation of reality. So some of the proof relies on assumptions that cannot be proven, like there will always be a period where the network is stable and all messages will be delivered. It's an assumption. However, some of the properties, like non-self-slashability, does not rely on any of that. And you can always refine the model to getting it closer to reality. So you can always apply an improvement to it. So concluding on key takeaways, distributed protocols like the Ethereum consensus protocol are difficult to reason about, and they're really full of corner cases because of this asynchrony of the messages. So identifying all the corner cases is just not feasible, it's not possible. What we can do is what we did, which is define a list of properties, put together mathematical proofs showing that these properties are guaranteed no matter what, in a way, so excluding possible corner cases. However, there are limitations, one of which I mentioned before. Sometimes we model the system, we model reality, and this model is not always a true representation. So there is, but as I mentioned, there is work that can be done to refine the model. And this concludes my talk. A few references up for you. Thank you.